Welcome. Take a deep breath and settle in. You know that feeling when you look at a huge, tangled circuit diagram and just feel instantly overwhelmed? Well, you are in exactly the right place. Today, we're taking those intimidating, abstract electrical math concepts and turning them into purely intuitive physical logic. No high-pressure lecture here, just a calm, step-by-step breakdown of the fundamental laws that quite literally power our modern world.
To get us there, here is our roadmap for today. We'll quickly cover the fundamentals of electricity, classify our network elements, establish the rules of circuits, introduce reactive circuits, and finally, dive into analyzing transient responses.
Let's kick things off with Section 1, the fundamentals of electricity. Before we can even begin to analyze a network, we have to ground our math in physical reality. We need to define the fundamental forces at play, starting at the absolute baseline: charge. Charge isn't just some random variable in an equation. It's the physical, characteristic property of particles that makes all electrical phenomena possible. Protons give us a positive charge, electrons are negative, and neutrons, well, they're neutral. In our equations, we measure this foundational property in coulombs.
Now things start getting really interesting when that charge actually moves. Moving charge is what we call electric current. It's literally just a measurement of flow over time. You've probably seen the math. I equals dq over dt. That's really just a fancy formal way of saying current is the rate at which a specific amount of charge passes by a point in one single second. We measure this flow in amperes.
But what actually pushes that current? Why would the charge even want to move? That, my friends, is electrical potential, better known as voltage. Voltage is the actual work being done to move those charges from point A to point B. Think of it like water pressure in a pipe. It is the driving push inside the system, and we measure this potential difference in volts.
Finally, when you combine that pressure, the voltage, with the flow, the current, you get electrical power. Power tells us how fast that electrical work is actually getting accomplished. It's the so what of the circuit. Just multiply your voltage by your current and boom, you have your power, which we measure in watts.
All right, moving right along to Section 2, classifying network elements.
So we know the basic forces. Now let's look at the actual pieces on the board and how they shape those forces. The most crucial distinction here is knowing whether a component is actively supplying power or passively receiving it. Active elements, like your independent voltage and current sources, are your engines. They push energy into the system. Passive elements, on the other hand, just react to what the active elements provide. Resistors dissipate energy, while inductors and capacitors store it.
We also have to classify these elements by how they behave. Linear elements are great because they play perfectly by the rules of proportional math. If you double the voltage across a linear resistor, the current doubles right along with it, perfectly satisfying Ohm's law. Nonlinear elements, like diodes, throw a bit of a curveball because that relationship is not a straight line. But to keep things clear and simple today, we're mostly going to stick to those predictable linear elements.
Up next, Section 3, the rules of circuits. With our active and passive elements defined, we need to establish the ground rules for how they interact in a calm, steady state. And there is this profound yet incredibly simple truth we have to follow. What flows into a junction must flow out. This is Kirchhoff's current law, or KCL. The algebraic sum of all currents meeting at a node is exactly zero. Energy doesn't magically vanish. If 5 amps flow in, a total of 5 amps must find their way out through the connected branches. If we zoom out from a single node to an entire closed loop, we hit Kirchhoff's voltage law, or KVL. This law shows us that energy is always conserved across a closed path. The voltage you supply to the loop from your source matches exactly what drops across passive elements like resistors. The total algebraic sum of all voltages around that loop is zero. It's a perfectly balanced equation. Energy in equals energy out. And the beauty of these simple laws is how they build into brilliant shortcuts, like Thevenin's theorem. Instead of spending hours solving massive webs of resistors and sources, Thevenin proved you can simplify any complex linear network down to just one single voltage source and one single resistor. You just follow 3 low-pressure steps: isolate the network, find the open circuit voltage, and calculate the equivalent resistor. Suddenly, the wildly complex becomes incredibly simple.
Let's transition into Section 4, introducing reactive circuits.
This is where our journey takes a really fascinating turn. We are shifting from the steady, predictable state of simple resistors into circuits that react to time. There is a major paradigm shift here. Our basic algebraic equations now acquire an integro differential form. I know that sounds intimidating, but it simply means that the moment we add inductors and capacitors to the mix, time becomes a critical factor. We are gently stepping out of simple algebra and moving into the dynamic world of calculus.
This shift is huge. Resistive circuits are basically static, they're time-independent and dissipate energy instantly. But reactive circuits, they are completely dynamic and time-variant, because inductors store energy in magnetic fields and capacitors store energy in electric fields. They introduce a dynamic delay. They actively oppose sudden changes in current or voltage, creating a system that evolves over time.
Which brings us to our final part, Section 5, Analyzing Transient Responses.
So, what exactly goes down during that dynamic delay? What happens in those fractions of a second when a switch is first flipped? Let's think about an RL circuit, one with a resistor and an inductor. When you close the switch, the inductor fights the sudden rush of current. This creates what we call a transient state, a temporary, chaotic reaction before the circuit settles down. To understand exactly how the current behaves during this brief period, we are forced to solve a first-order linear differential equation.
But please don't let the calculus overwhelm you. We just follow a very logical, step-by-step path. First, use Kirchhoff's voltage law to formulate the equation. Then, solve for the complementary solution. This represents that temporary, dying-out chaos of the transient state. Next, find the particular solution, which gives you the permanent steady-state calm the circuit eventually reaches. Add them together, and you have the complete picture of how the current flows from the literal millisecond the switch is flipped until the end of time.
Now, if you have a circuit with all three passive components, resistors, inductors, and capacitors, that initial transient chaos is going to settle down in one of three distinct ways, depending entirely on the component values. It might be overdamped, slowly and steadily reaching its final state without bouncing. It might be critically damped, hitting that final state as fast as physically possible without overshooting. Or it could be underdamped, where the energy literally bounces back and forth between the capacitor and inductor, creating a decaying ripple before finally settling. This math dictates exactly how safely and smoothly our electrical systems power up.
As we wrap up today, I want to leave you with this final peaceful thought. We've just mapped out how flipping a tiny switch in a basic textbook circuit creates a brief, hidden moment of complex mathematical oscillation before finally finding balance. Think about that the next time you turn on a light switch. What unseen, dynamic forces are flowing, storing, and settling across the massive, interconnected electrical grids that safely power our entire world every single second? The math we explored today isn't just theory, it is the invisible heartbeat of our modern lives. Thanks for hanging out and learning with me today.